Hello viewers, in today's session we are going to discuss another important and conceptual problem from domain of functions, and here we have to find the domain of this function, that is f of x is equal to cos inverse greatest integer of 2x minus 3 over 5, right? So here we can see that here we have the combination of two important functions. The first one is the inverse cosine function, and the second one is the greatest integer function. So let us see how easily we can find out the domain of this function by using the definition of greatest integer function and some important concept from inverse trigonometric functions. So whenever we have to find the domain of some given function f of x, it implies that we have to find all the valid values of x for which the function is defined. Now here let us first see the inverse trigonometric function, that is cos inverse theta. Now we know that the range of cos inverse theta belongs to this interval, that is from 0 to pi, right? And here this theta must belong to this interval, that is minus 1 to 1. So cos inverse theta, it belongs to this interval, that is 0 to pi, whenever theta belongs to this interval minus 1 to 1. So theta must lie between minus 1 and 1. Now here if we take theta as the greatest integer of 2x minus 3 over 5, then our function, it assumes the form cos inverse theta, right? And here now we'll make use of this inequality, that is theta must belong to this interval, that is minus 1 to 1. So taking theta as greatest integer of 2x minus 3 over 5, over here we have minus 1, and then we have greatest integer of 2x minus 3 over 5, and this is less than or equal to 1. So now we have this important inequality, and we have to solve this inequality to get the values of x. So now to solve this inequality, we have to make use of one important result, which says that if we have this inequality, that is greatest integer of a, that is greater than or equal to minus 1 but less than or equal to plus 1, then this a must belong to this interval, that is minus 1 to 2. So here a should be greater than or equal to minus 1 but less than 2. So we'll make use of this result, right? So here our a may be taken as 2x minus 3 over 5. So here we have minus 1, and here we have 2x minus 3 over 5, and this is less than 2. So 2x minus 3 over 5 should be greater than or equal to minus 1 but less than 2. So now we have a simple inequality and we can easily solve it. So let us first multiply this inequality throughout by 5. So we have minus 1 times 5, and here we have 2x minus 3 over 5 times 5, and here we have 2 times 5. So here we have minus 5, here 5 and 5 get cancelled. We have 2x minus 3, and here we have 10. Now let us add plus 3 throughout. So we have minus 3 plus 3, and here we have 2x minus 3 plus 3, and here we have 10 plus 3. So 3 minus 5 is minus 2, and here we have this 3 and this 3 get cancelled, and we have here 13, right? Now let us divide throughout by 2. So we have minus 2 over 2, then here we have 2x over 2, and here we have 13 over 2. So this 2 and this 2 get cancelled, and here we have simply x, and here we have 13 over 2. So now we can see that our x, which constitutes the domain of this function, this x belongs to this interval, that is from -1 to 13 over 2. And remember, here -1 is included, while 13 over 2 is not included. So this is closed from this end and opens from this end. So now this interval can also be written as -1 to 6.5. So all the values of x which lies in this interval gives us our domain. So let us represent this interval on the real number line. So here we have 0, here we have -1, then we have 1, 2, 3, 4, 5, 6, and here we have 7, right? So 6.5, it lies somewhere here. So here we have 13 over 2, and we can draw a circle here. It implies that 13 over 2 is not included, and here we have -1, right? And here we'll draw a dark circle which suggests that -1 is included, right? So all the values which lies between -1 and 13 over 2, uh, it belongs to the domain of this function. So here we can easily see that -1 is included our domain. So let us take x is equal to -1 in this function. So we have f of -1, that is cos inverse greatest integer of 2 times -1 minus 3 over 5. So here we have cos inverse, this is -2 minus 3 over 5. So this is -5 over 5, that is -1. So here we have greatest integer of -1, and greatest integer of -1 is -1, right? Because the greatest integer of any integer is the integer itself. So here we have cos inverse -1, which is true, because theta belongs to this interval, that is -1 to 1, and here -1 and 1 both are included. So -1, that is x is equal to -1, is in the domain of the function f of x. Similarly, here we can verify that this point, that is 13 over 2, is not included in our domain. So let us find f of 13 over 2. So this is cos inverse, and here we have 2 times 13 over 2 minus 3 over 5. So we can see that 2 and 2 get cancelled, and 13 minus 3 is 10, and we have 10 over 5, that is cos inverse greatest integer of 2, this is 5 times 2, and greatest integer of 2 is 2, and we can see that 2 is not included in this interval. So we have to discard x is equal to 13 by 2 from the domain. So all other points which lies between -1 and 13 by 2 belongs to the domain of this function. So viewers, this is how we can find out the domain of this function, that is cos inverse greatest integer of 2x minus 3 over 5, and the domain is given by this inequality or this interval. Hello viewers, in today's session we are going to discuss another important and conceptual problem from domain of functions. right? And here we have to discuss this problem in which we have to find the domain of the function f of x, which is equal to sine inverse greatest integer of 5 minus 3x, right? So here we see that we have a function which involves two important functions in mathematics, that is the inverse trigonometric function, that is sine inverse, and the greatest integer function, right? So here we have the combination of inverse trigonometric function and greatest integer function, and we have to find all the valid values of x for which this function is defined, because the domain of functions implies that we have to search for all those values of x, the valid values of x for which the function f of x is defined, right? So let us see how easily we can find out the domain of this function. So here the first important concept is that the range of sine inverse theta is given by this interval, that is minus pi by 2 to pi by 2, when this theta belongs to the interval minus 1 to 1, right? So we know that the principal value branch of sine inverse theta is minus pi by 2 to pi by 2, and this is closed interval for all values of theta belonging to this interval, that is minus 1 to 1. So here if we take theta as greatest integer of 5 minus 3x, then this function f of x is equal to sine inverse theta, right? And this theta must belong to this interval. It implies that theta is greater than or equal to minus 1 but less than or equal to 1, right? And our theta is greatest integer of 5 minus 3x. So here we'll substitute greatest integer of 5 minus 3x, and here we have less than or equal to 1, right? So now we have an important inequality involving the greatest integer function. Now let us see how we can solve this inequality. So here we'll make use of this important result, that is if we have greatest integer of a is greater than or equal to minus 1 and less than or equal to 1, then the value of a, this is greater than or equal to minus 1 but less than 2, right? So when we have greatest integer of a greater than or equal to minus 1 and less than or equal to 1, then this a, which is inside the greatest integer function symbol, then this a is greater than or equal to minus 1 but less than 2. Or in other words, we can say that if greatest integer of a belongs to this interval, that is minus 1 to 1, then this a, it belongs to the interval minus 1 to 2, right? So here I will make use of this important result. So here our a is 5 minus 3x. So we can now form the inequality, that is minus 1 greater than less than or equal to 5 minus 3x, and here we have 2, right? So now we have this simple inequality, so we can now subtract 5 throughout. So we have minus 1 minus 5, here we have 5 minus 3x minus 5, and here we have 2 minus 5. So this is minus 6, and here this 5 and this 5 get cancelled, and we have 2 minus 5, that is equal to minus 3. So now we can divide throughout by this factor, that is minus 3, right? And the direction of the inequality get reversed. So here we have minus 6 over minus 3, and then the direction of this inequality get reversed. Here we have minus 3x over minus 3, and here we have minus 3 over minus 3. So here we'll get now 2, and here we have simply x, and here we have 1. So we can now write this inequality as x greater than 1 and less than or equal to 2, or in other words we can say x belongs to this interval, that is 1, and here we have 2 and this is closed, right? So this is open from this end, that is 1, and closed from this end where we have 2. So here 2 is included and 1 is not included. So we see that the domain of this function, it means we have to search for those values of x for which this function is defined, and we have arrived at this result, that is x belonging to the interval 1 comma 2. So the domain of this function is given by this interval, that is 1 comma 2, which is open from 1 and closed from 2. So let us represent this interval on the real number line. So here we have 0, here we have 1, here we have 2. So here 1 is not included, so we can encircle it, and here 2 is included, right? So all the values of x which lies between these two intervals except 1 and including 2, right? So the domain is given by this interval, and here we can easily see that x is equal to 1 is not admissible, because uh, when we take x is equal to 1 in this function, then we can see that f of 1 becomes sine inverse, and here greatest integer of 5 minus 3 times 1, and we have sine inverse, and this is 5 minus 3, that is 2, and greatest integer of 2 is simply 2, because we know that the greatest integer of any integer is given by the integer itself. So we have sine inverse 2, and from here we can see that the theta belongs to this interval, that is minus 1 to 1, right? So here we have 2, and 2 does not belong to this interval minus 1 to 1. So we cannot take x is equal to 1 in our domain. But 2 is included, because if we take x is equal to 2, then we have f of 2 is equal to sine inverse, and here we have 5 minus 3 times 2. So this is sine inverse, and 5 minus 3 times 2 is 6. So we have sine inverse, greatest integer of 5 minus 6 is greatest integer of minus 1. So this is sine inverse minus 1. So this is admissible, because here we have minus 1 and here we have minus 1, right? So 1 is not included, but 2 is included, and all the values which lies in this interval are also included. Hello viewers, in today's session we are going to discuss another important problem from greatest integer function, and here we are going to utilize one important property of greatest integer function to solve this given problem. So let us first to read out this problem. So here let xi belonging to the set of integers. So here z denotes the set of integers and xi belonging to the set of integers, where xi are the solutions of this inequality, that is minus 4 less than or equal to greatest integer of 2x minus 7 less than or equal to 3. Then we have to find the value of the cube root of half times the summation, that is sigma xi square. So here our aim is to find all those xi which belongs to the set of integers, and xi are the solutions of this inequality. So solutions of the given inequality. So our aim is to get the values of all xi which satisfy the given inequality containing the greatest integer function. So now we have this inequality, and we'll solve this inequality with the help of one important property of greatest integer function. And the property goes like this. If we have two integers, say n1 and n2, and n1 and n2 both belong to the set of integers, then the inequality, that is minus n1 less than or equal to greatest integer of a less than or equal to the integer n2, it implies that minus n1 less than or equal to a, that is less than n2 plus 1. So when we have n1 and n2 belonging to the set of integers, and we have an inequality of this type, that is greatest integer of a is greater than or equal to minus n1 but less than or equal to n2, then we have this number, that is a is greater than or equal to minus n1 but it is less than n2 plus 1, right? So here if we compare this inequality with this one, so when we compare this inequality with this one, then n1 is 4, and a is given by 2x minus 7, and n2 is equal to 3. And we can see that both these numbers, that is 4 and 3, belongs to the set of integers. So this inequality is similar to this one. So when we have two integers n1 and n2 which are associated with the greatest integer of a like this, then we have this number a as greater than or equal to minus n1 less than n2 plus 1. So here a is 2x minus 7. So now this inequality gives us minus 4, because n1 is 4, and here we have a is 2x minus 7, and here we have n2 plus 1, n2 is 3, so we have 3 plus 1. So now we have minus 4 less than or equal to 2x minus 7, that is less than, here we have 4. So now this inequality implies this one, that is minus 4 less than or equal to 2x minus 7 less than 4. Now to solve this inequality, we'll add 7 throughout. So we have minus 4 plus 7. Here we have 2x minus 7 plus 7, and here we have 4 plus 7. So this is 3, 7 minus 4, here 7 and 7 get cancelled, 2x, and here we have 11. Now we can divide throughout by 2, right? So dividing throughout by 2, we have 3 by 2, here we have 2x over 2, and here we have 11 over 2. Now this is 3 over 2, here we have simply x, and here we have 11 over 2. So the solution of this inequality is given by x greater than or equal to 3 by 2 and less than 11 over 2. So now we can also write this inequality as 1.5, because 3 divided by 2 is 1.5, and here we have x, and here we have 11 over 2, that is 5.5. So x belongs to the interval, that is 1.5 to 5.5. And remember, here we have the interval closed, and from here we have the interval open. So 1.5 is included, but 5.5 is excluded. So now let us represent this solution set on the real number lines. So here we have minus infinity, here we have plus infinity, and here we have 0, then we have 1, then we have 2, 3, 4, 5, and then we have 6. Right now, see, x belongs to the set that is 1.5 to 5.5. So 1.5, it lies somewhere here. So here we have 1.5, that is 3 over 2, and 5.5, it lies between 5 and 6. So here we have 5.5, that is equal to 11 over 2. Right, so here we have to find all the integers which lies between 1.5 and 5.5, because see, in the problem we are given that xi belongs to z, where xi are the solutions of the inequality, right, and xi belongs to the set of integers. So here between 1.5 and 5.5, we can count all the integers. So here the integers are 2, 3, 4, and 5. So xi are given by 2, 3, 4, and 5. It means x1 is 2, x2 is 3, x3 is 4, and x4 is 5. So here we have 4 integer solutions of this inequality. So now we have to find the value of this expression, that is the cube root of half of sigma xi square. So we can now write sigma xi square as x1 square plus x2 square plus x3 square plus x4 square, because here I runs from 1, 2, 3, and 4, because we have 4 integer solutions of this inequality. So we have here 2 square, then we have 3 square, 4 square, and 5 square. So 2 square is 4, 3 square is 9, this is 4 square 16, then we have 25. So this is 13 plus 16, that is 29, and 29 plus 25 is 54, right? So the value of sigma xi square is 54. So half of sigma xi square is equal to 54 over 2, that is 27. And now we have to find the cube root of half of sigma xi square, that is 27. And the cube root of 27 is equal to 3, right? So the value of this expression is equal to 3.